Just make sure you understand that for the exam. Okay, so when we actually calculate out solve out this integral, we should get, if the rate's going to positive 4, we expect that to go to positive infinity. So how do we handle this antiderivative? Does undoing the product work? Did someone do undoing the product? That might work. I don't know. But this is a rational function. Degree of the numerator is the same as degree of the denominator. What do? Long divide. That's how you start this one. Long division. Now, undoing the product may work. Did anyone successfully do undoing the product rule? Let's see if we get the same thing, okay? Undoing the product rule could work. I don't know, but this is probably easier. So we're going to need 4 here. 4 times x plus 1 is 4x plus 4. Subtract, you get negative 4. So this is the same as 4 minus 4 over x plus 1. That's the result of the long division. The quotient is 4, then the remainder over the divisor. And so then the antiderivative is 4x minus 4 natural log of x plus 1. And we're going to take the limit as a goes to infinity from 2 to a. Okay, so undoing product rule. Did you get the same thing? Those who did undoing the product rule? Did you get 4x minus 4 natural log of x plus 1? That's what you got? Okay, so undoing the product rule will work on this if you do it right. But this is probably much faster. Yeah? You got the same answer? So is u equals x plus 1? Yeah, that's good too. Yeah, so if you do u equals x plus 1, that'll work. That's good. Yep. Didn't see that. Yeah, if you do u equals x plus 1 and do the math right, that's absolutely fine too. So actually, you had three ways to do this. 3 ways to do this. Okay, and so then we're going to do this equals limit as a goes to infinity, and right away we see 4a. So that shows right there, just writing that much shows divergent, but we'll keep writing here. 4 ln of a plus 1 minus 4 times 2 plus, this doesn't matter, 4 ln of 2 plus 1. Okay, so this goes to infinity. This likewise goes to infinity. So actually what we have is infinity minus infinity. Okay, and so don't worry about this, but in order to do this, you have to use so infinity minus infinity is an indeterminate form. It's an indeterminate form, and you have to use an exponent technique to get this in the form of a fraction. So if you do an exponent, you can get this in the form of a fraction using the rules of logs, and then you can, by L'Hopital's rule, show that this indeed does diverge, goes to infinity. Okay, so let's just, for grade's sake, if you got this plus 4 for that, and then if you correctly did the antiderivative and you got this far, say another plus 4 for that. And then now we're at 12 points, so everyone add 8 to your score. So 4 points if you put diverges, 4 points if you were able to get this, or, so yeah, if you got this, that's 8, right? Any way you could. If you got that antiderivative through any technique, then that's plus 8. If you got this far with long division, and somehow messed this up, then that would be worth 4. And then add 8, and that's out of 20. Everyone gets 8 points for free. Does the grading scheme make sense? So this part you're not responsible for. But this does get large. It goes infinity. I'll show you after class. If you want to see this, I'll show you after class. So use exponentiation and rules of logs to make this a quotient. And then you can use L'Hopital's rule. And you'll see that it does indeed get big. Yeah. -2. Okay. Got your grade? So turn it over face down. Make sure the right heading is on the upper right-hand corner, name, date, and your recitation, and then pass the way we normally pass.
They haven't put the limit, -2.
For that part?
Yeah, there's no limit. And they put infinity up there instead of...
Yeah. So, okay, keep passing, but just, we can't plug infinity into expressions. So I tried to emphasize this last time. You can't just do 2 to infinity and plug in infinity. We have to evaluate a limit. We have to say, where's this thing going? What's the limiting value? Okay? So, for the sake of the test, not for today, just keep passing in, but for the sake of the test, that you will lose credit if you do not change that to some variable and take the limit as that variable goes to infinity. So this is the right technique for that. We're going to get our expression in terms of A, and then the end we're going to evaluate the limit. Make sure you do that. We don't plug infinity into things. We let a value get very, very large, and we see what the behavior is. We see where it's heading to. That's a limit. Does it make sense? So on the exam, if you left off the limit, and then you just worked with this expression and infinity, that you won't get full credit. Okay, you won't get full credit. Okay, other questions about this? Okay, so let's go over some web work. Okay, so I'm going to get through as many of these as I can. Many of them I'm not going to finish. I'm just going to get started until we get to a point where it's pretty basic. You should be able to see through to the solution. Okay, so this was the first one. So I picked all the ones that there was the lowest success on. So let's see, okay, so we'll have these. I'll have the table here ready to go. So that they're saying use a table for this, and what we want to do is we want to get rid of the e to the x first, right? We want to get rid of the e to the x first. So we're going to change the variable to u. So we'll let u equal e to the x. And so what does that mean? That means that du equals e to the x dx. Okay, so a big part of this is just really being confident with your algebra and your ability to substitute things that are equal, right? If one thing equals another, then anywhere you see the one thing, you could substitute the other. That's what equality means, right? So notice this. Do you see this right here? What does e to the x dx equal? It equals du, right? And we see this, so we see the exact same thing right there. There's e to the x dx. So what does that equal? Du. So more than half the battle here is just performing correct algebra and just being confident with substitution using equality. So e to the x dx, it equals du. So I can put it in there. And so what I'll end up having is my new integral in terms of u will be 3 du over 3 What's e to the 2x? U squared. So now I look for my table. That's something like the denominator would be like a squared minus x squared. So which one is that? Right here. So there it is, right there. See it? That's the one I want. And what's my a squared is 3, so my a is the square root of 3. A squared is 3, so a would be the square root of 3. So it's going to be 1 over 2. 1 over 2 square root of 3. Natural log, absolute value. U plus square root of 3. U minus square root of 3. And then I'm going to substitute back. We know u was, what did I call u? E to the x, right? E to the x. So I can just change those u's to plus c. Questions on this example? I'll try to get to as many as I can here. What's that? I'm sorry? Did I forget it? Yeah, so there should have been a 3 here. So I did it without doing the 3, so that should be right there. Thank you. Yeah, if I make a mistake, please speak up. Thank you. That should be 3. Just carrying the constant 3. Yes, please. So that the name of the kind of integrals is table integrals, meaning you have to have a table to do it. You have to memorize the identities. That's it. So table integrals means you're using a table. So I will, if that's on the test, you'll have to have either one or a table of these to use. Yeah. Yeah, if it matters. Yeah, It's just like you got what work problems wrong if you needed them. Yeah. So many of you experienced that. Well, if this is positive, if this is always positive, then you don't need it, right? So if that expression is always positive no matter what you put in for x, then you don't need them. But it's never wrong to put them, so just always put them. But you only put it when it's an antiderivative is an ln. ln doesn't always have absolute values on the argument. It's when you take an antiderivative and get natural log that you need absolute value. Okay. Other questions on this one? Okay, next one. All right, this one, another table. So we're looking for, this is going to be, that's what we're thinking, a squared minus, square root of a squared minus u squared over something squared. So just, that's also going to be from this list. Looks like, where is it? 65? Yes, thank you. This one. So we're looking to set it up like this. So, but we have 2x squared. It just wants x squared. So that's where we have to make our initial. So we want our u squared to be 2x squared. All right, that means that first of all, x squared equals u squared over 2. That'll be for the denominator. And then we got to get what dx is. So we'll solve for x. Solve this for x. We get a square root of u squared over 2, which is u over the square root of 2. So dx is du over the square root of 2 also. Now we're ready to set up so the negative 2, we can just take that out here, negative 2 like that, and then square root of 7 minus u squared over u squared over 2. And then dx is du over the square root of 2. So let's combine all these all these here to get one constant, so we don't have to worry about it. So negative 2 over 1/2 is negative 4. So it looks like this whole thing is negative 4 over the square root of 2 is what I get for all that. So it's going to be negative 4 over the square root of 2 times what I get from the table. What did you say, 65? So it's going to be 65 up there. All right, so negative 1 over u square root of 7 minus u squared minus, so this is now arc sine, right? Arc sine is different than 1 over sine. Make sure it's arc sine there. So then we got the arc sine or sine inverse of u over what's a? Square root of 7 in my example. All right, questions so far. So then we still have one more step to revert back to x. Is it good so far? I got it not right down there. Sorry. Always end up in the lower part of the screen. Good so far? All right, so the next step, so substituting back in, I'll do it in blue right here. Negative 4 over square root of 2. What is u? Square root of 2x. Negative 1 over the square root of 2x. Square root of 7 minus 2x squared minus sine inverse of square root of 2x over square root of 7. That one, a little bit, you got to be really careful with all your substitutions. Are we good? We go on? Because it's a different book, right? So we don't use the Stewart book. Yeah. Our book is Briggs and Cochrane. Other questions? Yeah, every book has its own numbering on their table. Yeah? Yes, so there's probably some simplification. This one here? You think about that? Yeah, but then you got to be careful because that applies to the second one too. But I did that. So this rad 2 here. Are you talking about this one? I took out. That's what I did. I took out negative 2. Oh, I see. Okay, yeah. So that you wanna factor out 2 out of these two things, and then that's a radical 2 outside, and then you don't have to do substitution. Yeah, it works. It works. It's great. Okay, other questions? Okay. Next one. Okay. So what do we got? Y equals the cube root of y plus 4. Is it undoing the chain rule? And if not, what small change would have to be there in order for it to be undoing the chain rule? This would have to be y squared. If this was y squared, it'd be undoing the chain rule, right? That's what we always look for first. Okay? But it's not. It's y plus 4. So maybe undoing the product rule would work for this, but it's not the easiest thing to do. Do you see what we can do? Let u equal, so it's similar to the example I did in class last time, u equals. So the problem with this here is the cube root of a sum. That's locked. We can't do anything with that. But if we have the cube root of just a single term, then we may be able to work with that in terms of multiplying times other things. But the cube root of y plus 4, we can't, that's like, we're locked into that. So by making u equal to y plus 4, then we're going to have the cube root of u, and that can be something we might be able to work with. Okay, so we need y, and we need dy. So y is going to be u minus 4. dy from this is just going to be du. Now we got everything we need. So we got integral y is u minus 4 cube root of u times du. Did it help? And you see that it helped. Because what can we do? So it's similar to the example I did last time, except we did this where we got a single thing like this in the denominator, and we could split it up. Here, we can just do what? Distribute, right? We can just distribute this now. This is u to the 1/3. So we get u to the 4/3 minus 4u to the 1/3. Home free. Maybe undoing the product rule works for this. In fact, it probably does. If you let f equal y and g prime equal cube root of y plus 4, probably undoing the product rule would work. But this also works. I think I prefer this a little bit easier. Questions on this one? And then you can take it from there. That's real easy, right? And then just substitute back in y plus 4 everywhere there's a u. Next one. Last chance. Questions on this one? Okay, here we go. So I see 2 sine squared plus 3 sine in the denominator. And that reminds me of quadratic expression, right? A quadratic expression. So I want to make u equal to sine x. Then du equals cosine x dx. And then, so you could solve this for dx, but what's easier to do is recognize, look, there's cosine x dx. Look at the integral. Cosine x dx, which equals what? Du, right? So this is du, so in that integral we can make it du. So then what we get is 1 over 2u squared plus 3u du. How do we do this? Is it undoing the chain rule? No, we'd need something like 4u plus 3 in the top, right? If we had 4u plus 3 or some multiple of that in the numerator, it would be undoing the chain rule. But we don't have that. Yeah?
You could plot the u and then use the partial fractions thing.
Yeah, it factors, right? So we got the denominator has a greater degree than the numerator, so we're going to factor out u. And you're off to the races with partial fractions. Partial fractions. Right? Partial fractions, you can do it when the degree of the denominator is greater, and the denominator factors. So you got to have both those things happening. The degree of the denominator has to be greater, and it has to be able to factor at least into 2 factors like this, and then you can do partial fractions. Questions on that one? Are we good? Yeah. Maybe. I picked all the ones, so I got a bunch more. Hopefully that'll be in the list. And if not, we'll do it after class. Next one. So I'll just talk about this. So I'm looking for what? Square root of a squared plus u squared, right? If we're talking about a table of integrals. So a squared plus u squared. So I'm going to let u equal Natural log of x, du equals 1 over x dx. Lo and behold, what do you see? 1 over x dx. 1 over x dx. So there it is. So it's going to be negative 9, 4 plus u squared du. Questions? Last chance on this one. So then that's the table. You're just looking for the form that's simply square root of a plus x, a squared plus x squared. Okay, next one. Okay, so we could do u squared equals u equals 3x, which would mean u squared would be 3x, which would mean u squared equals 9x squared. And then you could take it from there. You'll have your dx will be 1/3 du, so you have an extra 1/3. Or I guess you could do what they suggested. You could factor 9 out of this, which would come out as a 3, and then you wouldn't have to change it. So if you just factor 9 out of these two, then under the square root, that would come out of the square root as a 3. And then you'd be ready for the table. You wouldn't have to do a u sub. Either way. Next one. Improper. Let's make sure we do the most important proper one. This one. Okay, so for this one, we notice we have 1 plus x to the 6th. So if that were what? It would be helpful. If that were what? X. If that were something squared, we would have inverse tangent, right? So what squared would give us x to the 6th? If u was x cubed, then x to the 6th would give us u squared. And then we're going to have 1 plus u squared in the denominator, and we're thinking about using inverse tangent. But that's if this x goes away. So du equals 3x squared dx. So notice, x squared dx. X squared dx. So we can do du over 3 is x squared dx. So I can just bring 5/3 all the way out here, 5/3. So I pulled the 5 out, and then my x squared dx is actually du over 3. So then there's a 1/3 too, so I'll pull that out. And now I have exactly inverse tangent. It's going to 5/3. Okay, but we need a limit, right? So here's how we can handle this. We can say the limit as a, just do one limit as a goes to infinity, and then go from negative a to positive a. And so then this, as a goes to infinity, that will approach negative infinity, and that will go to positive infinity. So we can do it as one limit. Okay, and so then we'll have limit as a goes to infinity. Almost done. 5/3 tangent inverse of u. Okay, and so u is x cubed. So it doesn't change anything, but we just put it back in there. So u is x cubed. All right, so now you have to understand something about tangent inverse, right? Tangent inverse, what does it do? So you think about the unit circle. Since tangent gives you slope for angle, tangent inverse gives you angle for slope. right? So we think of all the slopes from negative pi over 2 to pi over 2. So you really have to know something about tangent inverse here. So all the slopes from negative pi over 2 to pi over 2. So the input into tangent inverse would be the slope. So as this gets very, very, very large, we're talking about making that input a very, very large slope, or like this. So what angle does that approach as the slope gets very, very large? That's what we're asking. As the slope gets really, really big, what angle does that approach? Pi over 2. So that's the limit as that gets big. And then minus. Now when that gets really, really big negative, what angle do we approach? That's the output of tangent inverse, is the angle that we would get when that input slope got very, very large negative. Negative pi over 2. Okay, I'll stick around for a couple minutes.